Welcome to Brain Vision.
Okay, so in this question, we have a ship that's sailing near a coastline. It is staying at a constant distance of d equals 600 meters. Um, and the ship is sailing past two radio towers on this coastline. One is at point A, and the other is at point B. Actually, I'm going to draw that a little bit further out just so we have some more space. Point B. And the distance between point A and point B is called L. L is 800 meters. And so the coastline is just a straight line, basically from A to B. And then the ship is sailing at 600 meters out from the coastline. So at point C, halfway between the two radio towers, the ship experiences constructive interference between the two signals. The two signals are at the same frequency, so they interfere constructively or destructively. But at the halfway point between A and B, along the ship's path, it experiences constructive interference. But then when it is straight out from point B, we call that point D. It experiences a minimum. It is the most destructive interference. And so from this information, we're supposed to figure out what the wavelength of the radio signal from the radio towers is. So what we need to do for this problem is we need to figure out what is the difference in distance that the signal has to travel from going between point A to point D and from point B to point D, and then we can use that to figure out what the wavelength of the wave is. So we need to figure out the distance between point D and B and from D and A. So B to D is just lowercase d because that's how far the ship is from the coastline. So that's pretty self-explanatory, but we can say that the distance from B to D is equal to 600 meters. And then we have to figure out what the distance from A to D is. And I kind of got a little bit ahead of myself, but I drew that the leg from A to B and B to D is at a right angle. So we have a right triangle here. So then we just use the Pythagorean theorem to figure out the distance from A to D. So one leg has a distance of L and the other leg has a distance of D. So we can just say that this is equal to the square root of 800 squared plus 600 squared. And if you calculate that, you'll get that the distance from point A to point D is 1,000 meters. Now, we need to figure out the difference between how far the radio signal has to travel from each tower. So we just take 1,000 and subtract 600 from it to get 400 meters. So the radio signal from point A has to travel 400 meters more than the radio signal from point D, or from point B. So that means that when they arrive at the ship at point D, they are out of phase with each other and they cancel as much as possible. They cancel perfectly. So this means that when they're 180 degrees out of phase like this, so you have, one wave is, if this is like the equilibrium line, one wave is going like this, and the other wave is going like this. They're 180 degrees out of phase, pi radians, but that also means that they are half a wavelength out of phase, because if you remember from previous chapters, but you'll remember that fact, and if you look at the graph, you'll see that, one wavelength, one wave is just shifted half a wavelength from the other. So this difference in distances that they have to travel is equal to lambda over 2. So to get lambda, we just multiply 400 meters by 2, and we can say that lambda is equal to 800 meters. And you're all set on this problem.